This is section 4 on chapter 1, complex number in the core 2 book, and this is on trigonometric identities or trig identities. And with complex numbers we have some trig identities. You've got trig identities from normal maths that you've done, but we've actually got trig identities with complex numbers. The reason being, if we call a complex number, or we write it in the form r cos theta plus I sine theta, we've got some trigonometry here, haven't we? We've got sine and cos, and we can use that along with some identities we've done before and actually prove these statements that if you have a complex number plus the reciprocal of that complex number, so plus the reciprocal, not multiplying by the reciprocal, you'll always get 2 cos theta. Okay, you can prove it by actually taking this statement here and multiplying it by 1 over that, and using the double angle formulas you can end up with this statement here. So this statement is always true for any complex number when it's written in this cos sine form. We can apply powers to that. So if you've got a complex number to a power plus 1 over the same complex number to a power, you'll get 2 cos. Now remember, the Moivre's theorem says that the power, then you multiply the argument by that power. And another trig identity is if you've got a complex number minus 1 over the complex number, you'll always get 2I sine theta, and again with powers z to the n minus 1 over z to the n will give you 2I sine n theta. Okay, so these 4 trig identities are going to be very useful to help us prove some other identities. And the types of things we're going to have to prove or show are going to be things like maybe cos to a power. Let's just write that to n, so that could be any power, or sine to a power. Let's put n there. Or it may be that we have some sort of multiple. So we're going to have some sort of statement that says, okay, one of these little things we've got here equals something and we need to prove it, or maybe we need to write it in a form that's all sine or all cos without the power. So a very simple example would be from U2 pure, where we have we know this statement. So cos 2 theta is 2 cos squared theta minus 1, or 1 minus 2 sine squared theta, or it could be written as cos squared theta minus sine squared theta. And you could actually prove this statement here using complex numbers. Okay, that's a very simple one. So imagine that 2 there was a 3 or a 4 or 5, or maybe we had something, we've got a power here like this, and we want to work out what we get on this side. They're the types of things we get. Okay, so in this example here, it says we need to use de Moivre's theorem to show that this identity is true. Now in these types of questions, we start with what's on the left hand side in this case, the most simple side of it, this simple expression, and we're going to get to this. Okay, so the first thing that we need to sort of work out on this question is, where would I see this in de Moivre's theorem? where would I see cos to the 6th theta? So just a reminder of what de Moivre's theorem states is that if we have a complex number written in this modulus argument form like this, and we raise it to a power n, and that's equal to the modulus raised to the power n, and then the arguments multiplied by n, like this. Yeah, so I would see cos 6 theta, it would appear over here on this side. So what I'm going to do is I'm going to write down de Moivre's theorem almost like the other way around. So cos 6 theta, so this is a bit I'm interested in, plus I sine theta, well, using de Moivre's theorem the other way around, that will be equal to cos theta plus I sine theta, all raised to the power 6. Okay, so I'm using it starting from this side, saying, right, this is where I'd see cos 6 theta here if n was 6, and then I can use it this way around. So let's just put an arrow to show that we're using it this way around. And on these types of questions where you see a multiple of theta, this is the approach that we take. So start by using de Moivre's theorem almost like in reverse. Okay, so that's step number 1. Step number 2 now is we are going to use the binomial expansion on this. So we're going to expand it. Now, I quickly want to find the coefficients of the binomial expansion. So I'm just going to use Pascal's triangle like this. I could use the NCR notation, but I just find this slightly quicker because it means I don't need to actually then calculate them on a calculator. So we're down to power 4, power 5, so these are just the rows of Pascal's triangle, power 6. So these are going to be my coefficients here. So 1, 6, 15, 20, 15, 6, 1. Okay, so I'm now ready to expand. Let's highlight it, this side here. So I'm going to write the expansion of that. So let's just write down here cos theta plus I sine theta, always to the raised to the power 6, is going to be this. So it's going to be cos to the power 6 theta, coefficient of 1. Then the next term is going to have a coefficient of 6. So that's going to be 6 cos to the power 5 theta. And then I sine theta. Okay, I'll put that in brackets. Right, next term. This will have a coefficient of 15. It will be cos to the power 4 theta, and then I sine theta squared. Now, it's really important that the second part of the bracket here, the I sine theta, we put in brackets, because when we square it or cube it or do it to any power, we need to do the power of the whole thing. So we don't just square the sine, we square the I as well, and that's going to make a difference to the signs of the numbers, whether the term is going to be real or imaginary. So we'll carry on down here. So coefficient of the next term is going to be 20. So I'm up to the middle now. And that'll be 20 cos cubed. So that's going down in power. So remember, with the binomial expansion, this first term is going to start at the highest power and go down. The second term is going to start from the lowest power and go up. So we're now up to I sine theta all cubed. And then the next coefficient is going to be 15. And it'll be 15 cos squared. So we're now down to cos squared. And then I sine theta to the power 4. Then the next term will have a coefficient of 6. Let's try and get 6 done properly. So 6. Still not tidy enough. Let's try that again. So 6, and that will be cos theta, and then I sine theta to the power 5, and then the last term is going to be I sine theta all to the power 6. Okay, so the next step now is we want to simplify all of this. Okay, so the first term is going to be cos to the power 6 theta. Now the second term, okay, when I multiply this out, I'm going to put the I at the front. So I'm going to put I and then 6 cos to the power 5 theta sine theta. Okay, so I can see clearly this is an imaginary term. So the first term is real, the second one is imaginary. The next term, now when I expand the brackets here, it'll be I squared sine squared. Now I squared is -1. So actually what happens to the third term is it will become -15 cos to the power 4 theta sine squared theta. And this term here is real because we had the I squared. Okay, let's move on to the next term. Here we've got I cubed sine cubed when we expand those brackets. Now I cubed is -I, so I'll need to put a negative sign there. So -I, so again I'm going to put the I at the front in front of this term, and then it'll be -I 20 cos cubed theta sine cubed theta. So I see that this term is imaginary, and maybe you begin to see the pattern. Real term, imaginary term, real term, imaginary term. So I am expecting the next term to be a real term, and that's when I have this term here. When I expand those brackets, that's going to be I to the power 4 sine to the power 4. Now I to the power 4 is just 1. So that means that the next term will, it won't change the sign, it's going to be a real term, and that will be 15 cos squared theta sine to the power 4 theta. Then we move on to the next term here. Now we'll end up with I to the power 5. Now the thing with I, we should know this already. So if we go up in powers, I cubed, I to the power 4, and so on. Well, I know that I squared is -1, I cubed is I to the power 4 is 1. What happens when I get to I to the power 5, it sort of cycles around again. This now becomes I. So I to the power 5 is just I. Then I to the power 6 is going to be -1. So you can see there's like a cycle of 4 terms. These 4 terms here. Okay, where we just cycle round and around. So if you've got like a big power of I, keep taking off multiples of 4 until it becomes one of these. So if you just take 4 away from the power, I to the power 5 is the same as I to the power 1 basically, which is just I. So in that term, just like the others, I'm going to write the I at the front. So plus I and then the 6, and then it'll be cos theta and then sine to the power 5 theta. Then the very last term here, this will be I to the power 6, sine to the power 6. So if I take 4 away from the power, I to the power 6 is the same as I squared, which is -1. So that becomes negative sine to the power 6 theta. Now, if we look at the original question, we want to find out what cos 6 theta is, okay, which is here. And that is the real part of that expression, the cos 6 theta. The sine 6 theta is the imaginary part of that expression. So what I'm really interested in is what is the real part when this is expanded. So I'm going to color code it. So everything that's green, I'm going to, or real, sorry, I'm going to highlight in green. So I have real, real here, and then real here. So these are the terms I'm interested in. These 4, they're all real, whereas all the other terms, the ones where I put the I's in the front, these are all imaginary. So these match up with the sine 6 theta. So really what I could write down now is this statement, that cos 6 theta, so if I just equate the real terms, so equating the real terms, cos 6 theta is cos to the power 6 theta minus 15 cos to the power 4 theta sine squared theta plus 15 cos squared theta sine to the power 4 theta minus sine to the power 6 theta. So really what I've done here is I've equated the real terms on both sides. Now we're on to our last step now, because you'll notice it says cos 6 theta and everything here is in terms of cos theta. There's no sines here, and I've got sine in my expression. So I've got sine squared here, I've got sine to the power 4 here, I've got sine to the power 6 here. So what I'm going to use is the fact that sine squared theta is equal to 1 minus cos squared theta. I'm going to make that substitution to get rid of the sine and change them to cos. Now this bit is actually quite a bit of expanding brackets and simplifying things, so we'll try our best. So cos to the power 6 theta minus 15 cos to the power 4 theta, and then we replace the sine with 1 minus cos squared. Then we've got plus 15 cos squared theta. Then we've got sine to the power 4. Now that's the same as sine squared squared. So it's the same as 1 minus cos squared theta, all squared. Yeah, when you square something and square it again, that's the same as doing power 4. And then the very last term, where I've got minus sine to the power 6, well, that's the same as 1 minus cos squared theta cubed. If you square something and cube it, it's the same as doing power 6. So the next part now is going to be to sort of expand brackets and simplify. So now we're going to have, if I expand the brackets, 15 or minus 15 cos to the power 4 theta, and then plus 15 cos to the power 6 theta. So basically I've just expanded these brackets here. Then I need to multiply this by these brackets expanded, so I now need to expand that. So it's going to be plus 15 cos squared theta. So if I expand these brackets here, I'll get 1 minus 2 cos squared theta, and then the minus cos squared theta times by the minus cos squared theta is going to give me plus cos to the power 4 theta. So I'm going to have to expand that in a moment. And then the last bracket, this will probably be the longest one, I need to sort of multiply out this bracket. I need to cube it. So the easiest way to do that is to think about what this would be if we multiply it by 1 minus cos squared. That would be the easiest way to do it. And then if we do that, there's going to be the minus there, of course, because there's a minus here in the front. And multiplying that out, we'll get 1 minus 3 cos squared theta. So I'm not going to go through all of the multiplying out. That's something you can do. Plus 3 cos to the power 4 theta minus cos to the power 6 theta. Okay, right, we're now ready for the last step, which is to say what all of this simplifies to. So let's start with the cos to the power 6. I've got a cos to the power 6 here. I've got 15 of them here, so that makes 16 of them. Now when I multiply this out with this term, I'll get another 15 cos to the power 6, and then that's 31 of them, and then minus, so that becomes another cos to the power 6. So I'm now up to 32 lots of cos to the power 6 theta. Okay, and that sort of matches up with this, so that's looking good so far. The next thing that we're going to be looking at then is the cos to the power 4 term. So we've got negative 15 of them here. And then if we expand these brackets, so when I multiply this term with this term, I'll have another negative 30 lots of cos to the power 4. So I've got negative 15 minus another 30, so that's minus 45 lots. And then from here, the minus here will mean I'll end up with another, taking away another 3 lots. So I'm now down to negative 48 lots of cos to the power 4 theta. Okay, again, it's looking good because that matches up. So now we'll look at the cos squared terms. So we're going to have 15 of them from here when we multiply out those brackets. And then because we've got minus and minus here, that's adding another 3 lots of cos squared. So that will give us 15 plus 3, 18 lots of cos squared theta. Okay, again, that matches up with what we were expecting. So we should now just have a 1 left over. And if I have a look, here we have it here, the minus 1. So we've proved that statement as required. So we could just put QED or hence cos 6 theta equals all of this here. But we've got to the statement as required. So just to run through the steps again, think about where you see this statement in de Moivre's theorem. Now this may be a sine, a multiple of theta to do with sine, so something like sine 5 theta, for example. Use de Moivre's theorem almost like backwards and say, well, what power does this need to be? Then do the binomial expansion on it. If it's a multiple of theta to do with cos, then you pick out the real terms. If it was a multiple of theta to do with sine, then we would pick out the imaginary terms. So for example, if this question was instead, show that sine 6 theta equals something, then we would start by picking out everything that's in blue. We don't need to write the i's because we're basically equating the imaginary terms, and simplify like before using this identity. Or it may be that you use cos squared equals 1 minus sine squared, so that you get your expression all in terms of sine or all in terms of cos. Okay, so in this example, we've got this cos to the power 5 theta. We want to express it in this form here, and we're going to find the values of a, b, and c when we do that. So it's like it's an identity. So basically, we've got cos to the power 5 theta is equivalent to a number cos 5 theta plus a number cos 3 theta plus a number cos theta. And our job is to work out what this side of the identity is, and in doing that we'll find the values of a, b, and c. And it's a really neat little method. Now we're going to start by using this identity over here, because I notice I've got cos in that identity. I'm starting with cos. You'll see why in a moment. So if I start with that identity, so z z plus 1 over z is 2 cos theta. What I can do is I can, if I divide both sides by 2, I'll get half z plus 1 over z equals cos theta. And now I'm going to do power 5 to both sides. So half z plus 1 over z to the power 5. I suppose I should use an identity sign. Okay, now can you see we've got the question we want here. Yeah, so can you see that? So we're basically going to be dealing with this side and see what we can do with that side. And we'll see it works out really nicely. So next step, we're dealing with the left hand side now. And if I do power 5 of both sides, so I'll get half power 5 z plus 1 over z to power 5. Okay, and if I do that, 2, 4, 8, 16, 32, so 1 over 32 z plus 1 over z to the power 5. Now what I'm going to do now is take this, I'm going to expand it using the binomial expansion. Now we could use like NCR when we're expanding this and work out the coefficients, but I'm just, because it's such a low power, I'm going to work out the coefficients by using Pascal's triangle. So I've already got power 3, power 4, so I know the coefficients are going to be this. Yeah, it's quicker probably than using NCR, although you could write NCR down when you're writing the question, but I've got the coefficients here, so I can use those. So now let's expand that. So I've got 1 over 32 times by the expansion of that, so that would be z to the power 5, coefficient 1, plus 5 lots of z to the power 4 times by 1 over z to the power 1, plus 10 times by z cubed times by 1 over z all squared, plus 10 z squared times by 1 over z cubed, plus 5 z. I'll rub that out to give me some space. I know what the coefficients are now. So that was 5z times by 1 over z to the power 4 plus 1 over z power 5. Okay, so all of that is the cos to the power 5 theta. Now here comes the neat bit. We're going to group together some of these terms. Now, well, all of the terms are going to pair up. This term can pair up with this term. Now the reason we're going to do that is so that we can use this identity here. They're all going to pair. Let's color code this. That will pair up with that. You'll see it in a moment. And these two will pair up. Right, so let's pair them together. All we're doing is just rearranging it and see what we get. That's in a bracket. So we get z to the power 5. Then the last term, also in green, will be 1 over z power 5 like that. Okay. The next pair, I'm going to have 5 lots of, now the one in orange here, that will cancel down to be z cubed. So that'll be z cubed. And then over here, this will cancel down to be 5 1 over z cubed if you cancel that. So plus 1 over z cubed, you can probably see what's happening here. Then the last two in blue that pair together, 10 lots of, that will be at z plus 1 over z once it cancels down. Right, now we can now use this identity to simplify. So I've got, remember the 1 over 32 from the start? This first term here is going to become 2 cos 5 theta. Yeah, look at that, compare it to this. So 2 cos 5 theta. This one here is going to become 2 cos 3 theta. And then this one here will become 2 cos theta with a 10 in front. So plus 10. Yeah. Now let's go back. Have I missed coefficients out? I'm just going to step back a bit. I think I may have missed the coefficient out. Right, okay. So, or I may have been right, I don't know. So 2 cos 5 theta. Oh, I see. And then plus 5 times 2 cos 3 theta. That's better. Plus 10 times 2 cos theta. Okay, and then once we simplify that out, we get the answers. So we'll get 1 over 16 cos 5 theta. Then the next one is going to be, well, we've got 5 times 2, which is 10. So you'll have 10 over 32, which is 5 over 16. So you'll have 5 over 16 cos 3 theta. And then the last term here, you're going to have 20. You'll have 20 over 32, which is 10 over 16, which is 5 over 8. So I'll have plus 5 over 8 cos theta. And here we go. We've done the identity. Yeah, and we found the values of A, B, and C. A is 1 over 16, B is 5 over 16, and C is 5 over 8. Okay, now if the identity we had was sine 5 theta instead, then we would be using this identity at the start and this one towards the end when we pair things together. So just to recap, what we did was we said, okay, I've got cos to the power 5. I can see cos is here. So basically I'm going to do this bit over here to the power 5. So I wrote that identity down. I divided both sides by 2, so I've got cos theta. Then I did power 5 both sides. I want to work out what this is. It's basically this here. Okay, and then we used the binomial expansion to multiply that out. It's like substitution. Basically, you substitute in a complex number and then substitute it back at the end because it's easier than writing sine, cos loads and loads of times. So you just substitute to something simple, do the working, and then substitute back. Similar to integration, where you use you do integration by substitution, where you make u equal to something. It's a similar idea that you take something complicated out and you replace it with something simple. You do the working and you substitute back at the end. Okay, yeah, and then once we did the binomial expansion, we paired terms up because those pairing of terms with the same powers allows us to substitute back here. Yeah, so we did that and then substituted back here, simplified it, we get our final answer. Okay, part A of this example is very similar to the last one. The last one was cos to the power 5 theta. This is sine to the power 4. This is the format that we need to get it in. So we're going to take the same approach. So we're going to start by using this identity here, since we have sine. So step number 1, we're going to write down z minus 1 over z equals 2i sine theta. The bit we're interested in really is the sine theta. So we're going to divide both sides by 2. So z minus 1 over z is I sine theta. And then we're going to do power 4 to both sides. So we'll get half to the power 4, which is 1 over 16. Then we'll get the z minus 1 over z to the power 4. And then we'll do power 4 the other side, so you'll have I to the power 4 sine to the power 4. Okay, now I to the power 4 is just 1, square root of minus 1, squared and then squared again. So you just end up with 1. So we've got 1 over 16 z minus 1 over z to the power 4 is sine to the power 4 theta. So just like last time, we're interested in expanding this side and seeing what we get. So if we do that, we get 1 over 16, and using a binomial expansion. Now again, I could use NCR, but it's just as quick, or I think quicker, to do Pascal's triangle down to the 5th row. So I know that the coefficients, because I'm doing power 4, are going to be 1, 4, 6, 4, 1. That's quicker. So I will have z to the power 4. So that's the coefficient of 1. Next one, 4 lots of z cubed minus 1 over z. So we need to take care with that because we have negative 1 over z here. We need to make sure that goes in the bracket. Okay, next one, I'm going to have plus 6 of z squared. Let me just tidy up that. That's a z cubed there. And then minus 1 over z squared plus 4z minus 1 over z cubed, and then the last term is going to be minus 1 over z power 4. Okay, so we want to pair up the terms. Now what we need to watch out for is that these negatives here, they're going to change some of the signs when we do that minus 1 over z to a power. So for example, the first, we want to pair them up, so we've got z to the power 4. Now the last term here, when we do the power, that will become positive. So this thing here will become positive 1 over z to the power 4. So plus 1 over z4, so that's that pair done. Okay, right, let's have a look at the next pair. Now the next pair is going to be this and this. Now this will simplify to z squared, but negative here. So I'll have negative 4z squared, and over here this will also be negative. This will also be negative 4z squared. That's what it will simplify to. So I'm going to put minus 4, and the pairing is going to be z squared plus 1 over z squared. So just make sure you're clear about that, the negatives. And then the last pairing, well, there's only one left on its own. We've paired up, that's paired up with that. This one's paired up with this. That just leaves this one floating around on its own. Now, the squaring of the minus 1 over z will make it positive. So I'll have 1 over z squared. That will cancel out with a z squared, just leaving me with 6. So plus 6. Okay, so now we're ready to simplify that even further, or to substitute back. So the z to the power 4 plus 1 over z to the power 4, that will become 2 cos 4 theta. So 1 over 16, and the first pairing becomes 2 cos 4 theta. The next pairing is going to be minus 4 times by this. Now z squared plus 1 over z squared becomes 2 cos 2 theta. And plus the 6. And then we can simplify that So 2 over 16 becomes 1 over 8 cos 4 theta. 4 times 2 is 8. 8 over 16, that becomes a half. And then the 6 over 16 becomes 3 over 8. So this is our final answer here, and we found the values of D, E and F. So that's part A. Now in, oh sorry, I've got the wrong sign here. That should be minus, because I have got a minus here. So I should have a minus there. Sorry about that. And last thing in part B, we're going to integrate sine to the 4. So we're not going to integrate that. We'll actually integrate its equivalent. So we're actually going to integrate between 0 and pi over 2, 1/8 cos 4 theta minus a half cos 2 theta plus 3 over 8 d theta. Okay, and this isn't too hard. So using the chain rule or reverse chain rule, cos 4 theta, that will become an 1/8 times a quarter sine 4 theta. The next term will become a half divided by 2, or times a half, sine 2 theta. So sine 2 theta. And then the 3 over 8 will just become plus 3 over 8 theta. So now we just substitute in those values. So we substitute in pi over 2 here, here and here. Then we substitute in 0 in the same places. And that will give you a final answer of 3 pi over 16. I'm sorry, I'm not doing the working. I just haven't got enough space to do it. So 3 pi over 16. So that second bit of the question does rely on stuff that you've done from pure year 2. And in pure year 2, you'll learn about integrating and differentiating sine and cos, and how to use the reverse chain rule to integrate things like cos 4 theta or cos 5 theta or sine 3 theta or sine 4 theta, that type of thing. Okay, should now be in a position where we can do exercise 1D on pages 14 and 15.